Hello and welcome to the S Chemistry lecture series. In this video, we're going to look at chapter 15, section 3. So we're going to continue our discussion on hydrocarbons, but we're going to switch our focus from the alkanes to the alkenes. So still hydrocarbons, so we're still in the same chapter, in the same functional group, but this is going to be a different type of hydrocarbon. Now, if we remember from chapter 14, alkenes are going to be compounds with the general formula CnH2n. So the reason why we have two less hydrogens than we do in the alkanes is because alkenes are going to have a double bond in them. Now, in general, alkenes could have multiple double bonds, although most of the alkenes we're going to see and the ones with the CnH2n general formula are going to be alkenes with just one double bond. So anytime we add a double bond to a compound, we're essentially losing two hydrogens. So if we have a very simple compound, right, like ethane, when ethane is created, when we draw its Lewis structure, it has 6 hydrogens because those carbons need to each have 4 hydrogens, or 4 bonds, making them have 3 hydrogens. If we add a double bond between the carbons to make this ethane into ethene, an alkene, that carbon now already has 2 bonds, meaning that it can only have 2 hydrogens attached to it. So whenever we go from the alkane version with the same number of carbons, in this case the alkane means C2H6, to the alkene version with a double bond, we are going to lose 2 hydrogens during the creation of that double bond, because that gives these carbons an extra bond that they have now, meaning 1 less hydrogen each that they can form. So when these carbons are created in alkene, the carbons that have the double bond on them are going to be sp2 hybridized, meaning that their shape is going to be trigonal planar. And they're going to have 120-degree angles. So that's a result of the double bond. Again, if we have a longer alkene, this will only apply to the carbons with the double bond on them. And so because alkenes are sp2 hybridized, because they have the double bond and therefore less hydrogens than the alkanes, they're known sometimes as unsaturated hydrocarbons. We talked about how alkanes were known as saturated hydrocarbons because they have the maximum amount of carbons that they could, hydrogens that they could possibly have. Alkenes are unsaturated hydrocarbons because they are, in essence, missing hydrogens. The double bond takes the place of what could be hydrogens, and therefore they're unsaturated. They don't have the full amount of carbons we could possibly have. And we see this trend with any alkene. For example, if we have C6H14, which is hexane, the alkene version of that, with 1 double bond, will be C6H12, hexene. So we see that loss of 2 hydrogens there. And this is going to be always the case with alkenes with 1 double bond, which are going to be most of the ones we see in the test. Now, you could have 2 or 3 or 4 double bonds in a larger molecule. And all that will do is, for every double bond we will have 2 less hydrogens. But let's go back to our PowerPoint here. So, that's a quick review of alkenes. How do we get alkenes, right? Because we discussed how alkanes are made through a process called fractioning, and we divide them out of crude oil. Well, alkenes are a byproduct of oil manufacturing as well. Now, they're not normally found in crude oil, but we can make them out of the compounds found in crude oil. So most crude oil is only, we discuss alkanes. So I'll put a little note here. Crude oil is usually some mixture of alkanes No, most of the crude oil is not going to have alkenes in it, but we can manufacture those alkenes through a process called cracking. Cracking is the processing of a crude oil to make alkenes. In essence, what is going to happen is that we're going to get these large, very useful hydrocarbons in crude oil, and we're going to break them down into smaller, more useful compounds. So very not useful hydrocarbons, very large hydrocarbons. Like here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is decane. Example here. This is decane. So this is decane, which is C10H22. So decane is very not useful at all. It's not something that we will use to do a lot of things or do a lot of reactions in chemistry. So we can undergo the process of cracking with decane and break it down into smaller compounds that are more useful. During the process of cracking, a large alkane, which is going to be our reactant here, decane, for example, being one such a compound. So a large alkane, which was our reactant, is going to be heated, which, remember our little discussion of our key here, double underline means that heating is a condition for our reaction here. So the large alkane needs to be heated and passed over a aluminum oxide catalyst. So aluminum oxide, which is here, has a dotted line because it's a catalyst for the reaction. Not a reactant, not a product, but a catalyst, but a necessary catalyst. So when we heat up a large alkane over an aluminum oxide catalyst with a lack of oxygen, so that's another condition here, with no oxygen present, meaning this has to be in a container that has been devoid of oxygen. What's going to happen is that compound is not going to burn because there's no oxygen there. What's going to happen is that compound will crack. When a compound cracks, when a large alkane cracks, the resulting products here in bold are going to be a smaller alkane and an alkene. Now, where exactly the large compound cracks, that's not something that's within the scope of our class. We're not going to learn to figure out where it's going to crack because that's very difficult and it's actually not very predictable. But the important thing here is that when we crack a large alkane, which is our reactant, we're going to get a smaller alkane and an alkene as our products. In this case, the smaller alkane that comes out of the decane is this compound right here, which if we count, we have 1, 2, 3, 4, 5, 6, 7. So this is heptane. And an alkene, which is this right here, which is 1, 2, 3, 4. And actually, yeah, 1, 2, 3, 4, which will be 1, because that's 4 is butene. And 1 butene because that double bond is a carbon 1. So this is 1 butene and decane that we get out of this cracking reaction. So we're going to break apart that compound and create an alkane, a small alkane, and an alkene out of that much larger alkane. So this is how we make alkenes to use in chemistry. What reactions then can these alkenes undergo? Because this is a reaction, cracking is a reaction that makes alkenes. But how do we create compounds from alkenes? Well, alkenes are one of their main reactions because of that double bond is going to be what we call addition reactions of alkenes, or the addition reactions. Most alkenes are going to undergo addition reactions because of the pi bond on the double bond. We have discussed, or very quickly discussed, in chapter 14, how the double bond on an alkene is what we refer to as an area of high electron charge. So an area of high negative charge. So this double bond right here, or in any alkene really, is an area of high negative charge because we have one pi bond and one sigma bond, or in total 4 electrons. This double bond in an alkene is going to be more negative than, say, the single bonds on the compound. So double bonds in alkenes are going to be areas of high negative charge, which are going to be attractive to nucleophiles, to things that are positively charged. So what happens during an addition reaction? During most addition reactions, what's going to happen is that the pi bond in the double bond is going to be broken, and 2 new atoms are going to be added where the pi bond breaks. The sigma bond will still be there in the products, but the pi bond is broken, and we'll get the addition of 2 new bonds to the one to each carbon. That's why we call this an addition reaction. We grab a small molecule, either made out of 2 of the same atom, like here we represent that by ZZ, or 2 different atoms, here we represent that by XY, and we add them across the double bond. We break the double bond and we add that compound. Now, this is the type of reaction, but I will say there are 4 different types of addition reactions we are going to study with our alkenes here in this curriculum. The first is the addition of hydrogen gas, whereas this is a type B type of reaction. So here we classify these as either type A on the top or type B at the bottom. Type B is when we're adding a molecule that has 2 of the same atom, whereas type A is when we're adding a molecule with 2 different atoms. And you'll see why this is important later on when we look at the individual reactions. So in this first reaction, the addition of hydrogen gas, it's a type B reaction because hydrogen gas is made out of 2 of the same atom bonded together. So we'll be adding hydrogens, so Z will represent hydrogen here. So we will essentially be adding hydrogens where the C's are. We are also going to look at the addition of a hydrogen halide. Remember, a hydrogen halide is a compound made of a halogen and a hydrogen. Halogen being X being either chlorine, bromine, iodine, or fluorine. So when we add a hydrogen halide to an alkene, again, that pi bond is going to break, and instead we're going to get those 2 different atoms added across where that pi bond used to be. So X will be H here, Y will be our halogen. So if this was HCl, X will be Cl. So that's a type A type of reaction where the atom that's being added has 2 different atoms, or it's made out of 2 different atoms. The addition of steam is also a type A reaction. Remember that steam is water, right? And you might say, well, a water molecule is not made out of 2 atoms, made out of 3 atoms, 1 oxygen, 2 hydrogens. So how does it fit this type of reaction? Well, when we look at water in an addition reaction, what we're looking at is that we have hydrogen bonded to a hydroxide, OH. That's still water, but essentially we're bundling up the O and one of the H's together and treating the other hydrogens separately. So when an addition reaction happens with steam, we're going to break that pi bond, and then we're going to add a hydrogen on one side and a hydroxide on the other, creating an alcohol. And we'll talk about why that creates an alcohol in a little bit. And then finally, the 4th type of reaction is when we add aqueous halogens. Halogens being the X X molecule, because the halogens are all diatomic. So X2 could be Cl2, it could be Br2, I2, or F2. So we could add a halogen across that double bond and end up with 2 copies of the halogens added across where that pi bond used to be. So these are all addition reactions. Why? We're adding a small molecule to a larger molecule, in this case an alkene, by breaking the pi bond and adding essentially one part of each of those molecules, small molecules, to each carbon that used to have the pi bond. So let's look at all the individual types of addition reactions. First, we have the addition of hydrogen to an alkene, and this process is also known as hydrogenation, right? Hydrogenation is just a common name for this process. It's actually used a lot to turn liquid oils into things like margarine. So liquid oils can become solid oils because most oils that are liquid, what we usually call the healthy oils, are alkenes. They have unsaturated hydrocarbons. That's why we call them unsaturated fats. Whereas margarine and most solid oils are alkanes. That's why we call them saturated fats, because most of them don't have double bonds. So we can undergo hydrogenation with liquid oils like seed oils to convert them into things like solid oils like margarine. Now, hydrogenation, how does it work? Well, during this reaction, what we are going to do is that we are going to grab hydrogen gas, which is going to be one of our reactants, and mix it with an alkene, which is our other reactant. So we're reacting hydrogen gas with an alkene. During this reaction, that mixture needs to be heated. So we're going to grab hydrogen gas, heat up the alkene, and mix them together. Once we do that, we are going to pass this mixture that has been heated as our condition, right? Because heating is a condition. And we are going to pass it over either a platinum or a nickel catalyst. Now, this is not platinum and nickel. This is an or. It could be a platinum or a nickel catalyst. Both of them will work. And again, this has a dotted line because it is a catalyst for the reaction. What's going to happen once we do that is the addition of the addition reaction is going to happen, and it's going to break the double bond on the alkene, or the pi bond actually on the alkene. So if we have ethene, very simple alkene, we are going to break one of the two double bonds, the pi bond, and that's going to cause the hydrogens to be added over that pi bond. So when we react hydrogen gas with an alkene over a platinum or nickel catalyst and heat, we are going to break that double bond. And I'm going to use 2 different colors here. We're going to break the double bond. One hydrogen will be attached to the one carbon on one side of where the double bond used to be. And then the other hydrogen will be attached to the other hydrocarbon where the double bond used to be. So we're adding, that's why it's called addition reaction, we're adding the hydrogen to the larger organic compound by breaking that pi bond. Hydrogenation, again, is very commonly used in the food industry, so this process is used a lot in the food industry because, again, plant oils like seed oils will usually have double bonds that we can break when we do this. One of the important things to understand here is that when hydrogenation happens, we go from a alkene to an alkane because we're breaking the double bond and adding hydrogen. So I mentioned how it's important to view reactions in organic chemistry as the transformation of one functional group to another. Well, when we react alkenes through hydrogenation, through the addition of hydrogen gas, we are turning an alkene into an alkane. And that's very important to realize. So the alkane, which should be bolded, and I can really tell if it is or not here, that alkane that we're creating is our product here. So that alkane is our product. All right. So that's our first type of addition reaction. The next type is the addition of the hydrogen halide. So if we look at this slide, we can see that we are now adding something that doesn't have just one type of atom like hydrogen did. We have two different types. We have here our, let me get my different colors here. We have our hydrogen in the hydrogen halide bonded to a halogen. And again, the halogen could be a number of different things. In this case, in this example we're seeing here, the halogen is bromine, and that bromine is bonded to a hydrogen. So what do we get when we do addition of hydrogen halides? Again, one of our reactants is going to be an alkene, which makes sense considering we're studying the reactions of alkenes. That alkene is usually going to be in the gas form. Most alkenes are either liquids or gases. Oops, let me make that smaller. So we're going to grab this alkene in the gas form, and we're going to bubble it through a concentrated solution of hydrogen halide, meaning that this hydrogen halide is aqueous but concentrated. And that's very important. We need the hydrogen halide to be aqueous because the different hydrogen halides are all gases at room temperature. And this reaction will be very hard to do without water. So we're going to grab our alkene, which is our reactant in the gas phase, and we're going to react that alkene or bubble it. So essentially, literally what it sounds like, we're going to grab a tube of this gas, put it at the bottom of a beaker, and then we're going to bubble that gas through an aqueous solution, concentrated aqueous solution of the hydrogen halide at room temperature. And so those are our two reactants, our hydrogen halide and our alkene. And what that's going to create is a halogenal alkane. When this reaction happens, this is the conversion of an alkene into our product here, which is a halogenal alkane. Let me write that up here. So this is a conversion of an alkene into a halogenal alkane. Why? What happens in this reaction? What happens in this reaction is that the pi bond on the double bond gets broken, and then hydrogen gets added to one carbon, and bromine, or whatever halogen we happen to have, gets added to the other carbon. So we'll have our bromine here added to one carbon, and our hydrogen added to the other, creating the halogenal alkane. Now, why did I mention that it's important that this particular reactant that we're adding has two different atoms, not just both hydrogens that we saw earlier, but in this case, a hydrogen and a halogen? Well, because of this, with longer alkenes, we're going to have the possibility of creating isomer products. And there's that word again from chapter 14, isomers. And isomers are actually very important in organic chemistry because certain reactions are going to lead to more than one product. For example, imagine we have this compound right here. This compound is, oops, let me make it smaller. 1, 2, 3, 4, 5, 6. So hexene, because it has a double bond. That double bond starts at carbon 2, so this is 2 hexene. So when we react 2-hexene with HBr, we are going to get the addition of our bromine and our hydrogen. So we're going to turn this alkene into a halogen alkane. However, there are two different possibilities for this reaction. Why? That HBr could be added with the hydrogen on carbon 2 and the bromine on carbon 3, because it's HBr, or it could be added with bromine on carbon 2 and hydrogen on carbon 3. And actually should have flipped this now that I'm looking at my answers here. But so let me flip this just so it makes more sense with the arrows here. So on the top we have the product that would result from bromine being added to carbon 2 and hydrogen being added to carbon 3. While in the bottom side, we have the result or the product that will happen if we add a hydrogen to carbon 2 and bromine to carbon 3. Because HBr has two atoms that are different, one hydrogen, one bromine, we can add them in either direction and they'll give us two different results. When we add the bromine to carbon 2, we will get 2-bromohexane. Whereas if the bromine is added to carbon 3, like we have in the bottom here, we'll get 3-bromohexane. These are positional isomers of each other. So this reaction has a possibility of creating positional isomers. But it does depend on the alkene, because if we did that with ethene here, that we had in the first example, it doesn't matter whether we add bromine to this carbon or this carbon, because we will get the same molecule. We will get just bromoethane. Notice I'm not putting a number, because if I put the bromine on this carbon, it will still be 1-bromoethane or bromoethane. It wouldn't change. But because we have a longer chain compound, the hexene or alkene here, we can have positional isomers being created from this reaction. Anytime we have this addition reactions where the additive, the small molecule being added, has two different atoms, we are going to get positional isomers as products. Which leads us to a conversation about what in organic chemistry we call major and minor products. We already saw this with free radical substitution in section 14.2. We're now seeing it again in section 14.3, where we can get more than one organic product when we undergo a reaction. In addition reactions, when we have asymmetric additives, which are water and hydrogen halides, two possible products can arise from that addition because of those positional isomers. In this case, both the products are created. So when I say that we have two possible products here, the 2-bromohexane and the 1-bromohexane in this case, so this is a different reaction actually. So here we have 1, 2, 3, 4, 5, 6. So this is 1-hexene. When 1-hexene reacts with HBr, we get the possibility of two products. We can either get 2-bromohexane up here, or if the bromine is added to the first carbon, we will get here 1-bromohexane. So which one does get made? And the reality is that with a lot of these organic reactions, it's not that we get one or the other. The reaction creates both of these products at the same time. But even though both of the products are created at the same time by the exact same reaction, they're not created equally. These two products are created at different amounts. The product that we make more of is called the major product. Very obvious there. And the product we make less of, a smaller amount, is called the minor product. So the major product is made in larger amounts. The minor product is made in smaller amounts. They're both made, but in different amounts. In an addition reaction, the major and the minor product are going to be dictated by the position of the halogen. The major product is going to be the one that has the halogen, or the hydroxide if we're using water, and we'll look at the reaction in a second. But whether the halogen or the hydroxide bonded to the carbon with the highest number of alkyl groups bonded to it. So essentially, it all depends on what our additive is going to be added to. So again, major product is going to be the one with the halogen or hydroxide, depending on which one we're doing, bonded to the carbon atom with the highest number of alkyl groups. What exactly does that mean, and why does it happen? The why does it happen we're going to discuss in a little bit when we discuss the mechanism of this reaction, how this reaction happens. But let's discuss what this means exactly. Whenever we have an addition reaction of an asymmetrical compound, meaning HX, whereas X here can be either fluorine, chlorine, bromine, or iodine if we're doing a halogen alkane, or it could be hydroxide if we're doing steam or water. So this is the addition of steam. These are with the addition of a hydrogen halide. So what is going to happen here? The more carbonyl groups, alkyl groups, not carbonyl. The more alkyl groups we have on a carbon, the more stable the molecule is. So if whenever we add HX across a double bond, that double bond gets broken, C gets one carbon, will get the hydrogen, the other carbon gets X. Where X is what decides what the major product is. The more carbons are where X is, the more stable the compound becomes. So if X is attached to a carbon with one carbon chain and two hydrogens, that's the least stable. If that carbon has two carbon chains, and remember ours are carbon chains, two carbon chains added to it and one hydrogen, that's more stable. If X is attached to a carbon with three different carbon chains on it, that's the most stable. And I put that here. So this will be the most stable. So the more carbon chains, and remember, R is a carbon chain. The more carbon chains there are in the carbon that X is attached to, either the halogen or the OH is attached to, the more stable that compound is. Meaning that a compound that has X attached to a carbon with three carbons attached to it is going to be a major product over a compound where X is attached to a carbon with only one other carbon attached to it. This is what dictates a major versus a minor product. It's a comparison of stability. The more stable, the more likely it is to be the major product. So let's go back and look at that compound, those reactions we were looking at earlier. So if we look at these two compounds, this carbon right here is attached to a carbon chain on this side and a different carbon chain on this side. On the other hand, this carbon where the Br is attached to here is only attached to one carbon chain. So this is what we call a primary, and we'll discuss why it's actually called primary halogenoalkane, but we'll discuss that in the halogenoalkane chapter. This is a primary, where this is secondary, meaning we have two carbons attached to a carbon. That's why this is a major product. The carbon that the Br is attached to has more carbons bonded to it than in the alternative product. So what happens? The one with more carbons attached to it is the major product, whereas the one with less carbons attached to it is the minor product. They're both still made, but we're going to make more of this one and less of this one because of the amount of carbons attached to that carbon the Br is attached to. If we had OH instead of Br, it would be the same thing. So if this bromine was one of the other Rs, so one of the other halogens or hydroxide ion, hydroxyl group, should I say, because it's organic chemistry, it will still be the same thing. It's about what that group that we have now added, because it is an addition reaction, whatever carbon that group is added to needs to have the most carbons as possible for it to be the major product. Now, it is worth saying that if we look at the reaction we're looking at earlier, the two products here are both secondary. If we look at this carbon that this bromine is attached to, there are two carbon chains, two R groups attached to it. If we look at this carbon, also has two carbon chains. It doesn't matter how long those carbon chains are. It just matters that that carbon has two carbon chains on it. So these products, there is no major or minor product here. This would actually be 50-50. They will be made in the same amounts because they're both equivalent. They're both secondary carbons. They're both carbons with two other carbon chains attached to them. Unlike the one we're seeing in the last slide, where one was secondary and one was primary. So there was actually a different and therefore a major and a minor product. So now that we have that discussion of major and minor product, let's look at the other addition reaction that has this happen, which is the addition of steam. And like I said, here we're going to look at water as kind of a two-part molecule, even though it does have three atoms, one oxygen and two hydrogens. Instead of looking at water like this, which is what we've been looking at water like for the past 2 years, or year and a half, we're going to look at water as H bonded to OH. So the hydrogen is bonded to an OH. So it's a two-part molecule where hydrogen's on one side, hydroxide on the other. Water actually acts like this in a lot of different reactions, not just this addition reaction of steam, but also in hydrolysis reactions when it breaks something apart. So what we're going to do is that we're going to use steam in this reaction to break down an alkene or add it to an alkene and make an alcohol. So here's steam, which is just aqueous water, and oh, that is the wrong color. So here steam is going to react with an alkene. So those are going to be our reactants, steam with an alkene, and they're going to create a product that is an alcohol. So that's our product here, an alcohol. So we can view the addition of steam to an alkene as the reaction that converts an alkene into an alcohol. So it's very important, right, to do those changes in functional groups. Remember, an alcohol is going to be a compound that has an OH or a hydroxyl, is what we call that, a hydroxyl group on it, an OH group. So what we're using is we're using water as the additive in the addition reaction, where water is going to split into hydrogen and a hydroxide. The gaseous alkene has to react with steam. So this is a completely gas phase reaction where the alkene is a gas. And notice we're saying steam, not water, because that water also needs to be a gas. And they are heated. This is going to happen in very hot conditions to keep those gases under, the gas state. So we're going to get heated under high pressure. So that's the conditions for this reaction. Not only does this reaction need to be hot, it needs to happen at high pressures. And it's not happening in the presence of, again, another catalyst. This catalyst this time, though, is going to be phosphoric acid. So it's the first time we see a catalyst, though it's an acid, although they're pretty common in organic chemistry. Phosphoric acid is going to be our catalyst here. That's why it has a dotted line underneath it. It's necessary for the reaction to happen. It's necessary for the reaction to happen quickly. That's what it does. It doesn't get used up. But it's also necessary for the reaction to even happen. So because water is also asymmetric, just like we were looking at with the halogen alkanes, water is asymmetric. A little smaller. Because again, we have X bonded to H bonded to OH, so they're not the same atom or the same group of atoms on both sides. We're gonna get a major and a minor product. So for example, here, if we react 1, 2, 3, 4, so this is butene. So 1-butene, when it reacts with water, one of these carbons will get the hydrogen, one of them will get the OH. If we put the hydrogen in carbon 1, and the hydroxide in carbon 2, we get our major product, which is going to be 2-butanol. Right? So we get that 2-butanol, which is our major product here. Why is 2-butanol the major product? Because the carbon that the hydroxyl group is bonded to is a secondary carbon. It has 2 R groups, 2 carbon chains bonded to it. On the other hand, if we attach the hydroxide to carbon 1, we get 1-butanol. 1-butanol is still made, but it is the minor product because the carbon the hydroxyl group is attached to here is a primary carbon with only 1 R group attached to it. And remember, the more R groups are attached to the carbon the hydroxyl group is attached to, the more stable the compound creation, and so it will be the major product. So here we have a primary versus a secondary, so the secondary is our major product. But yeah, this is the reaction of steam with alkenes. The last addition reaction we're going to talk about is the addition of halogens to an alkene. Now, halogens are a little easier because they do not create major or minor products, since halogens, which are X2, and again, X being just any of the halogens, so it could be chlorine, bromine, iodine, or fluorine, are symmetric. So halogens are symmetric additives. They are exactly the same on both sides. We have X bonded to X, so that could be Br bonded to Br, or Cl bonded to Cl, etc., etc. So because they're symmetric, there is no two additives to be added here. They're both exactly the same, so the direction in which it's added doesn't matter. So what is going to happen here? We're going to bubble an alkene. So again, we're looking at a gaseous alkene. So let me put that on here if it wasn't obvious by the word bubble. So the alkene is going to be gaseous, it's going to be a gas. It's going to be bubbled through either chlorine or bromine solutions at room temperature. Meaning these are going to be aqueous chlorine or aqueous bromine. We are not going to do this reaction with iodine or with fluorine because It is a little more complex. Although if you're asked about them on the AICE exam, realize that it will be a critical thinking question, and you should treat it exactly like you will treat bromine or chlorine. So the alkene, which is our reactant in the gas state, is going to be bubbled through a solution, aqueous, either chlorine or bromine. And we could do either or. So these are our reactants. And they're going to be at room temperature, so we don't need any heating or any cooling here. And the addition reaction is going to add halogens to both carbons. Because the addition is symmetric, what our product here is going to be the creation of what we call a dihalogenal alkane. And remember, the prefix di just means two. So this is just a halogen alkane with two halogens on it. So if we reacted something like this will be 4 carbons. So this is 2-butene. So if we react to something like 2-butene with chlorine, what will happen is that the double bond, the pi bond on the double bond will break, and chlorine will be added to one carbon, and the other chlorine will be added to the other carbons that we have on the double bond. So we create from these alkene, from the alkene, which in this case is 2-butene, we are going to create a dihalogenal alkane. And because we're adding chlorine to both the carbons, it doesn't matter which one gets which chlorine, because we're going to get the exact same compound if we just flip the chlorines from one carbon to the other. Same thing happens here with this bigger alkene here. We have 1, 2, 3, 4, 5, 6, 7. So this is heptene. And the carbon, the double bond, sorry, is on the 1, 2, 3rd carbon. So it's 3-heptene. Now, if you haven't noticed, and I'm going to just bring in a little review here. These are actually also can have cis-trans isomerism. Here, this is the trans version. So it's trans 2-butene because one stick's going down, one methyl's going up. In this one, we don't just have 3-heptene, we have trans 3-heptene. Because if you notice again, one carbon chain is going down, one carbon chain is going up from the double bond. So this is trans 3-heptene, trans 2-butene. But again, is that going to change whether this was cis or trans? Is that going to change our product? Not really. The double bond's still in the same carbons. So the product will be the same. But it's important to, take the opportunity to review things like cis-trans isomerism. So if we have the trans 3-heptene here, when we add bromine to the double bond, again, we break that carbon-carbon pi bond, and we're going to add bromine to both the carbons. So we'll get a dibromo. So this will be here 3,4 dibromo heptane, because we're adding bromines to both the 3rd and the 4th carbon. I did forget to name this one right here, but this will just simply be 2,3 dichloro, because we have chlorine instead of bromine, butane. I notice that the names, the endings change to A and E for the products, because the products are dihalogenal alkanes, not alkenes. The reactants are alkenes because they have the double bond. But the addition reaction breaks that double bond. And so we end up with alkanes, dihalogenal alkanes in this case. So those are the 4 different addition reactions. Now this last one can actually be used as a test for alkenes. Why? If we focus on this bottom reaction right here, That bromine, that aqueous bromine that we have here, we learned in chapter, I believe it was chapter 12, that this aqueous bromine is orange in color. So when bromine is aqueous, it is an orange color liquid. Well, that orange color liquid, when it's reacted with the alkene, becomes a dihalogenalkane, which is colorless. So that orange liquid turns colorless when reacted to an alkene, which means that we can undergo something called the bromine water test. When we talk about bromine water, that's just another way of saying aqueous bromine. So Br2 aqueous is what bromine water is. So what is a bromine water test? Bromine water test is a test for alkanes. Bromine water, like we just discussed, is orange in color. Aqueous bromine is orange in color. If we undergo an addition reaction where the aqueous bromine is used up as a reactant, the solution is going to lose its orange color. If I grab an alkene, and I added to my aqueous bromine, this is Br2, let me use a different color here. This is Br2 aqueous. So if I grab my aqueous bromine and I add an alkene to it, and I will actually bubble the alkene through it, but same difference. What will happen is that orange solution will become colorless because I will create the dibromoalkene, which is colorless, it doesn't have a color. So what happens? We can use this as a test for alkenes. If we add an unknown to aqueous bromine and it loses its color, we know that unknown was an alkene. Whereas if we add an unknown to aqueous bromine and it stays orange, then we know that that compound was not an alkene because the alkene would have reacted with the aqueous water. So this is an example of an observation, right? And this is an example of what we call a test. Now, a test is just a fancy term for a reaction that we can see a change in. So we can use it to test for specific functional groups. So bromine water goes from orange, let me make this a little bigger. Bromine water is going to go from orange to clear, orange to colorless, as the addition of bromine proceeds. Meaning that an orange to clear solution, when an unknown is added to bromine water, is a positive test for an alkene. So the positive test would be the decolorization, is what we call it, of the bromine water, because it loses its orange color and becomes clear. So that's an observation here that we have. It's an observation that happens during the bromine water test. All right. So that's the reaction. That's what happens when each different additive is added to bromine water, to alkene. So we're going back. If we add hydrogen gas to an alkene, we get an alkane. But that needs to be heated with a platinum and nickel catalyst. If we add a hydrogen halide, an aqueous hydrogen halide, to an alkene in the gas state, we get a halogenal alkane. This reaction, because the hydrogen halides are asymmetric, can lead to a major and a minor product, which gets decided by whether the carbon is primary, secondary, or tertiary. Whether it has one carbon chain added to it, two carbon chains attached to a carbon, or three, which we didn't see. If we add steam, which is water in the gas phase, to a gaseous halogen under heat and pressure with a phosphoric acid catalyst, we get the addition of steam to the alkene, creating an alcohol, and again a major and a minor product because water is asymmetric. And then finally, if we add a halogen in the aqueous state to an alkene that's in a gas state, we are going to get a dihalogenal alkane, which there is no major and minor product. It's always one product. But this, if it's bromine specifically, the halogen, can be used to test for the presence of an alkene in an unknown, or a double bond in an unknown. So that's a what. What we're going to do next is we are going to talk about the why, the mechanism for this reaction. So the mechanism for the addition reactions, all four of the reactions that we just looked at, the reaction of alkenes with steam, alkenes with hydrogen halides, alkenes with halogens, and alkenes with hydrogen, all happen with the same mechanism, meaning that they all happen in the same way. The mechanism is known as electrophilic addition. Now, the names of mechanisms always have two parts to them. The second part of the word at least, is the type of reaction. So in this case, addition, because this is the mechanism for addition reactions of this type. Oops, that is not what I wanted to do. So the addition refers to the type of reaction, whereas the initial part, electrophilic, refers to the mode of the reaction. Mode meaning the how. So this is the mode of the reaction, or the mechanism essentially. And the second part is the type of reaction. We saw this very similarly with free radical substitution in section 2. Free radical was the mode, substitution was the type of reaction as a substitution reaction. So electrophilic addition, in the mode of this reaction, it's going to include an electrophile. Remember, electrophiles, oops, I missed a couple of letters there. Electrophiles are compounds that have a partially negative or full negative charge, partially positive or full positive charge that can accept electrons. That's why they're electrophiles, right? They're attracted to electrons, they're attracted to negative charge. And what does a double bond have a ton of other than negative charge? Remember, we talked about earlier how a double bond is an area of high electron density. It has twice the number of electrons as a single bond. So there are 4 electrons in a double bond. Makes it very negative, makes it have a lot of electrons, right? 4 electrons. So that area is very negative, meaning that electrophiles are going to be very attracted to that double bond. This can be explained the easiest with the hydrogen halides and with steam. Both hydrogen halides and steam are polar molecules. So hydrogen halides and steam both have a partial positive section. In the case of steam, the hydrogen is partially positive, and in the case of hydrogen halides as well, the hydrogen is partially positive because the bonds to hydrogen are polarized. What does that mean? That means that there's going to be an attraction between that partially positive hydrogen and our double bond. That's what makes the steam or the hydrogen halide a nucleophile. When it not a nucleophile, an electrophile, should I say. It becomes an electrophile because a partial positive charges will be attracted to the high area of electron density in the double bond. Halogens and hydrogens are a little harder to explain because hydrogen and halogen molecules are non-polar. These are both non-polar molecules. Let me write that on here. But these can still be polarized. Now, what do we mean by polarized? Something being polarized refers to a bond becoming polar or being forced to become polar by something else. In this case, what happens is that the very high area of electron of electron density, or the negative double bond, is going to polarize the non-polar bond. It's very similar to what happens with London dispersion forces, where because this area, it has a negative charge, or it's a high negative charge, it pushes away the electrons in the single bond between the halogens or between the hydrogens. When that happens, when the electrons in the bond are pushed towards the opposite end of the bond itself gets polarized, with the closest halogen or hydrogen, depending on what we're looking at, becoming partially positive, and the one that's farther away from the double bond becoming partially negative. That's what creates the electrophile with the halogen and the hydrogen. It is this polarization of the bond created by that negative area of the double bond. So the polarized hydrogens and the polarized halogen also act like an electrophile, being attracted to that negative area on the double bond. So let's talk about what actually happens with this mechanism, this electrophilic addition mechanism. Because this is the reason why it happens, but this is not the mechanism itself. Let's look at the mechanism itself. The mechanism, again, is going to be the same, whether it's a steam, hydrogen halide, or a halogen or hydrogen molecule. It's going to be the same because all of these molecules are going to have that partial positive, whether it's because of polarization or because they're already polar molecules. What's going to happen in an electrophilic addition mechanism is going to happen in two steps. So this is a two-step mechanism where the reaction or the mechanism happens in two phases. In the first step, what's going to happen is that the electrons on the pi bond of the alkene, of the double bond, are going to be attracted to that partial positive part of the electrophile, whether it's the bromine that's been polarized, or the hydrogen in steam, or the hydrogen in the hydrogen halide. The partial negative the negative electrons in the pi bond are going to be attracted to the partial positive section of the electrophile. So the pi electrons are going to look at that positive charge and they're going to be like, how you doing? Positive charge. And it's going to create or use the pi bond electrons to create a bond to the bromine. At the same time that that happens, the bromine bond is going to get broken. Or if this was steam, it will be the HO bond. Or if this was hydrogen, the HH bond. That bond is going to be broken heterolytically, and both of those electrons are going to be given to the other section of the electrophile. Now this creates a few things. Why? Because the carbon-carbon bond, the pi bond, is also broken. And only one bond is formed to that bromine. So this right here breaks the pi bond and creates a bond between the one of the carbons and the bromine. The electrons that are broken heterolytically in the electrophile bond go to one side of the bond, creating a negatively charged ion. Well, when bonds break heterolytically, we discussed in, I think it was an earlier section of chapter 14, when bonds break heterolytically, two ions form. A positive ion, a cation, and a negative ion, an anion. In this case, when the heterolytic bond breaks between the bromines, the negative anion is going to be made in the electrophile here. So we're going to have this this negative ion being formed for the bromine, the bromide ion, because it took the two electrons. But then when that pi bond got broken and the carbon-bromine bond got made, The other carbon in the double bond now only has 3 bonds, meaning it has a partial positive charge. It becomes a carbocation. This carbocation is what's known as an intermediate. An intermediate is a compound or a species which is formed in a particular step of a reaction mechanism, and they're stable enough to be a product and often have partial positive or negative charges or full positive or negative charges. But the carbocation is an intermediate because it could be isolated. It is a fairly stable species or fairly stable chemical. Can it exist by itself long term? No. But it's stable enough during the mechanism that we can identify it. So that carbocation is an intermediate and happens after the first step of the reaction, where the pi bond breaks, forms a bond to the bromine in the electrophile, or the partial positive side of the electrophile, and then the bond in the electrophile between the partial positive and the partial negative breaks, creating a full negative ion. That's step 1. Let's put that here. This is step 1. Now, we did say this is a 2-step mechanism, and that first step creates a carbocation, not a dihalogenal alkane in this case because we're using bromine. In the second step of this reaction, what's going to happen is that partial negative charge and that partial positive charge, existing so close together, are naturally going to attract each other. So that negative ion that's created is going to see that carbocation's positive charge, and it's also going to be like, how you doing? And it's going to use the lone pair of electrons that it originally took from the bond breaking heterolytically to create a bond to that carbocation carbon. The partial negative on the full negative on the ion, the negative ion, so I use this lone pair of electrons to create a bond to the positive carbocation. That bond in the positive carbocation is the bond to the second bromine in this case, creating our final product, which is our halogenal alkane. That's step 2. So step 1 is the creation of the carbocation and the anion, where step 2 is the joining of the anion with the carbocation to create our final product. That's the mechanism. This is a very, very common mechanism to be asked about in the AICE exam, especially in paper 2. So it's not just important for you to understand what's going on here, you need to be able to draw this mechanism. You need to understand both steps so you can draw this mechanism not just for the halogen, but also for the steam, if we have steam, in which case we'll just draw the H and then here an OH, and it will be the exact same thing with this bond being the partial positive and the partial negative. It will be the same if we have the hydrogen, where we will just have a hydrogen-hydrogen bond with the farther hydrogen being partially negative and the closer hydrogen being partially positive. And it will be the same if we had a hydrogen halide, like HCl, for example, where the Cl will be the partial negative and the hydrogen will be the partial positive. But the whole reaction is exactly the same. It's just what are we adding that changes. But you need to understand this mechanism. What are the important things to include here? We want to make sure we are including partial charges. So that partial positive and partial negative here, those are not just for show. Also, full charges. You cannot draw a carbocation without that positive. You cannot draw the bromine without that negative. Also, lone pairs. Now, you don't have to show every lone pair. Notice how I didn't show the lone pairs on the bromines here. But that lone pair that gets created when that bond breaks heterolytically, we need to show that. Because that lone pair is then used in the second step. So those lone pairs that are important need to be shown. And then also make sure that you have your curved arrows, and that those curved arrows start at electrons. Meaning that this curved arrow has clearly need to start on this double bond. This curved arrow clearly needs to start at this bond. This curved arrow clearly needs to start at the lone pair. And they clearly need to point at a specific atom. If this arrow pointed here to this bond, you would actually lose points. You need to make sure that that arrow is pointing at the carbon. All right? So it's just some important things to keep in mind when you're drawing this mechanism. And I can almost guarantee that you will need to draw this mechanism for your paper too, because this is an extremely common question on the test. Now, how does this mechanism explain the major and minor products? We talked about how these major and minor products are created and how they depend on whether the carbon that we're adding to is either primary, secondary, or tertiary. Well, that is actually explained by the mechanism because of that carbocation, that positively charged carbon on the compound. Steam and hydrogens will create major and minor products depending on whether the halogen or the hydroxyl group, which if I go back, you might have realized the hydroxyl group and the halogen are the partial negatives. So they're going to be that second ion that's created. So the bromine here could be OH minus if it was steam, or it could be Cl minus or Br minus if it was a hydrogen halide. So where that second halogen or that second ion is attached to, that's what's going to dictate our major and minor products. So the stability of these major and minor products, the reason why major and minor products exist, why they both get created but one gets created more, is the stability of the carbocation that's created in step 1. Whenever that bond breaks in step 1, I'm sorry I keep going back and forth, but whenever this bond breaks, we could end up either creating a carbocation here on this carbon or a carbocation here on this carbon. In this particular molecule, it doesn't matter because both carbocations would end up being primary with one carbon attached to that carbon. And there's no other difference here. They will both be primary, will be essentially the same molecule. But what if that wasn't the case? Carbocations are classified as either primary, secondary, or tertiary. Methyl will be when it's all hydrogens, depending on how many alkyl groups are attached to that positive carbon. So a primary carbocation will have an R group, only one R group. In this case, we show it with a CH3 attached to the carbon. A secondary carbocation will have two R groups attached to the carbocation. In this case, again, we show it with CH3s, but this could be a much longer chain. And then a tertiary one will have three different R groups attached to the carbon that is positive. So, what happens here? Carbocations are going to be more stable the more carbons they are attached to. They're more stable the more substituted is what we call it they are. The more carbon chains are attached to the positive carbon. So methyl carbocations, the ones where it's just three hydrogens, are the least stable, whereas tertiary carbocations are the most stable. They have the more carbon chains attached to the positive cation. This is all thanks to something we talked about in the last chapter, which is the inductive effect. And we talked about this in the last chapter. The inductive effect talks about how carbon-carbon bonds are non-polar. So what happens is that when we have a positive ion, the electrons in this carbon-carbon bond are drawn towards a positive ion. The more carbon-carbon bonds we have in that positive ion, the more electrons are drawn towards that positive carbon. And because that positive carbon has more electrons surrounded, the positive charge is less positive. Less positive means more stable. Because remember, charges are what guide chemical reactions. The less positive a charge is, we still see it as a full positive, but it's a spectrum. The less positive a charge is, the more stable that compound's going to be, because the less things that positive thing is going to attract. And so, the more substituted the carbocation is, the more positive inductive effect we're going to get, because you can have negative inductive effect, we'll talk about that later, but the more positive inductive effect we're going to have, which means the less positive the carbocation will be, and the more stable it will be. The more stable the carbocation, the more likely it is to form. And that makes sense, right? The more stable it is, the more likely it is to even exist. Which is going to explain why addition products with higher grade, higher tertiary, essentially, carbocations are major products. Carbocations that are tertiary are more likely to get created. And if they're more likely to get created, their product that they create are more likely to get created. So it's a comparison, right? If we have tertiary and a secondary, the tertiary is going to get created. If we have secondary and a primary, the secondary is going to get created. If they're both primary, then they're equally as likely to get created. So let's look at that in the actual mechanism. If we have this compound right here, which is 1, 2, 3, 4, 5. So this will be 2. Oh no. So this will be 3-methyl. Because we have that 1 carbon chain on the 3rd carbon. 3-methyl, 2, and this is 5, so pentene, because we have the alkene on the 2nd carbon, the on the 2nd carbon. So if we react 3-methyl 2-pentene with water, or with steam in this case, what's going to happen in that first step of the mechanism, I'll just put it here, step 1. So in that first step of the mechanism, we have 2 things that can happen. Either that hydrogen gets added to carbon 3 and we get a secondary carbocation out of it, because if that hydrogen gets added to carbon 3, and let me number these carbons. Here's carbon 1, 2, 3. So if this hydrogen gets added to carbon 3, that means the positive ion ends up on carbon 2. Or the positive charge ends up on carbon 2. If the hydrogen gets added to carbon 2, that means the positive charge ends up on carbon 3 in step 1. Both of those things can and will happen. But when both of these happen, the secondary carbocation that's created is less stable than the tertiary carbocation because of what we just discussed about the positive inductive effect. Well, that means that we're going to have more of this happening, creating the tertiary carbocation, and less of this happening, creating the secondary, because this is more stable, therefore more likely to exist. Now, this is not going to happen. No, it will still happen, but it will happen less. Well, then in step 2, when that hydroxide is added to the carbocation, with the tertiary carbocation, it's going to be added to carbon 3, creating the major product. Because there's more of these tertiary carbocation, more hydroxides get added to a 3rd carbon, and we get more of the product that is tertiary. Whereas in the secondary carbocation, which we get less of, we're still going to get hydroxides attached to it, creating our minor product, just less of it, where the hydroxide is added to the 2nd carbon, creating, in this case, 3-methyl 2-pentanol, again, because it's an alcohol, so it's pentanol, versus 3-methyl 3-pentanol. So 3-methyl 3-pentanol will be the major product because the carbon attached to, or the alcohol is attached to a tertiary carbon. And again, it's tertiary. Why? Because it has 1, 2, 3 R groups attached to it. Whereas the minor product will be the 3-methyl 2-pentanol because the alcohol is attached to the secondary carbon. Because that secondary carbon only has 2 R groups, 2 carbon chains attached to it. And makes the, why is that the case? Because this came from a secondary, and let me write that here too, this came from a secondary carbocation, whereas this tertiary alcohol came from a tertiary carbocation, meaning that this was more stable, more of it got made, and that's why this is the major product. All right, so this is how we explain that major and minor product of the reaction through the mechanism. This is why mechanisms are important. They help us understand how we get specific products in a reaction and why sometimes we get a major product and a minor product. Well, that's it for these type of reactions of alkanes. These are the addition reactions of alkanes and their mechanism. I know that this can seem like just 4 different unrelated reactions, but you got to realize these are all the exact same reaction with the exact same mechanism. What we are changing is just what we're adding. So view these mechanisms as related and it will make your life a lot easier. Well, that's it for this video on section 15.3. I will see you all in the next video for 15.4, where we'll talk about the oxidation reactions, a different type of alkene reaction.